Hello, my name is Gautam Das. Today I'm going to explain one of the general methods of preparation of aldehydes and ketones, which is oxidation and dehydrogenation of alcohols. Now first, oxidation of alcohols. First we take primary alcohol. Very simply speaking, if we show like this, primary alcohols have two oxidizable hydrogen atoms as shown in the red circle, and it can be easily oxidized to aldehyde and finally to carboxylic acid. Aldehyde also has one oxidizable hydrogen atom. Now primary alcohol, when treated with either of these reagents, which may be KMnO4H plus or K2Cr2O7H plus, potassium dichromate H plus, or CrO3 chromic anhydride H plus, that means acidic chromic anhydride, acidic potassium dichromate or acidic potassium permanganate, or CrO3 in presence of water and acetone, which is nothing but chromic anhydride and aqueous acetone, which is commonly called Jones reagent. With any one of these reagents, primary alcohol will finally form carboxylic acid via the formation of aldehyde. But with these reagents, the reaction cannot be stopped at the aldehyde stage. The final product will be always carboxylic acid containing the same number of carbon atom as the primary alcohol. The reaction cannot be stopped at the aldehyde stage with this reagent. Final product will be only carboxylic acid with the same number of carbon atom as the primary alcohol. Now coming back to the observation of this, when treated with acidified KMnO4, which you all know pink in color, it will form this colorless carboxylic acid and there is a brown precipitated MnO2. With acidified dichromate, which is orange in color, again the colorless solution of carboxylic acid, and we'll get a green coloration, which is due to the Cr+3, which may be chromium sulfate if sulfuric acid is used, or chromium chloride if HCl is used, and so and so. Now, oxidation of alcohols show alpha hydrogen isotopic effect. This is the alpha carbon. That means the hydrogen atom attached to this. These are alpha hydrogen atoms. Alpha hydrogen isotopic effect means the CH bond cleavage, this is the alpha hydrogen, will decide the rate of reaction. This will become more clear when we will discuss the explanation of the oxidation, mechanism of the oxidation rather. Now what is the application of this alpha hydrogen isotopic effect, which we say that the CH bond cleavage decides the rate of the reaction? That is evident if you consider the reactivity of alcohols. Which is evident in this. Among this, CH3OH is most reactive, followed by CDH2, where one hydrogen atom of CH3OH is replaced by deuterium. Then CD2H, two hydrogen atom replaced by deuterium. Then CD3OH, which is same as CD3OD, almost same, because this hydrogen atom has nothing to do with the oxidation, because this is not the alpha hydrogen atom we are talking about. This is because the CH bond energy is much less than CD bond energy. So we can easily break the CH bond compared to CD bond, and that's why this reactivity rate. Now coming back to the oxidation of primary alcohol again, as we have already discussed, with any of these reagents mentioned, the final product will be carboxylic acid. The reaction cannot be stopped at the intermediate stage of aldehyde. Now to stop the reaction at the aldehyde stage, if I want to stop the reaction at the aldehyde stage, we have to use PCC, which is nothing but pyridinium chlorochromate. Let me first show how it is formed. Sorry. This is our PCC. Now, aldehydes are susceptible to further oxidation. That's why conversion to primary alcohol to aldehyde is quite troublesome. The base reagent for this purpose, as I've already mentioned, is PCC, which is formed by mixing equimolar amount of chromic anhydride, CrO3, HCl, and pyridine. A simple acid-base reaction, then it will form an additive type of compound like PCC. Okay? Now this PCC is soluble in CH2Cl2 and any other organic solvents. So if our CH2OH is treated with PCC, the final product will be aldehyde and aldehyde only, and no further oxidation of aldehyde to carboxylic acid won't occur. Now instead of PCC, we can also use PDC. What is that? Which is pyridinium dichromate. Let me show its formation. It's almost similar to that of PCC. Or simply this. So PCC or PDC, primary alcohol will give only aldehyde. Now in this context, I want to mention one thing which is rather confusing. If we use chromic anhydride in presence of pyridine, pyridine is this, we already know. This is called Collins reagent, or even called Sarrett-Collins reagent. Then also primary alcohol will only give aldehyde and not carboxylic acid. So remember one thing, primary alcohol with Jones reagent, which is chromic anhydride in presence of water and acetone, will give only carboxylic acid as the final product. But primary alcohol with Collins reagent or Sarrett-Collins reagent or with PCC or PDC will give aldehyde. Okay? Now let's go to secondary alcohol. Oxidation of secondary alcohol. Now secondary alcohol, when treated with acidified dichromate, potassium dichromate, or acidified chromic anhydride or chromic anhydride in presence of pyridine, will only give ketone. Will only give ketone. KMnO4, on the other hand, can oxidize secondary alcohol to carboxylic acid. That we'll see in later application. But with these reagents, it can be only converted to ketone and no further oxidation possible. KMnO4, if used, then it can oxidize that ketone again via oxidative cleavage, that we'll discuss later on in the same class, to carboxylic acid. Now let's go to tertiary alcohol. Now 3-degree alcohol or tertiary alcohol oxidizes only using KMnO4H+. As I've shown here, this tertiary alcohol, I'm not showing the exact products, we'll come to the application later on. When treated with acidified KMnO4, KMnOH2SO4 heated for hours under drastic condition, there will be smaller acids formed. That means those acids will contain the less number of carbon atoms as the original alcohol, which are formed by the cleavage of carbon-carbon bonds. With acidified CrO3 or acidified dichromate, they are own Bendy reactions. Tertiary alcohol will only get oxidized using KMnO4H+. That means 1-degree or 2-degree alcohol, when treated with acidified dichromate, which is orange in color, there will be green coloration. Why? Because they will react and they will form Cr+3 as we mentioned before. While 3-degree alcohol, when treated with the same, there will be no green coloration. Why? Because 3-degree alcohol won't react with potassium dichromate. Cr+3 won't be formed. Now let us see some applications. Let's take some example. Let me do it first and I will explain. This will actually explain why with KMnO4H+, there will be cleavage and so and so. Now, I've taken the secondary alcohol which when treated with KMnO4, initially it will form this ketone, 2-butanone. But with KMnO4H4, it will further undergo oxidation. Now, ketone undergo oxidation via enolization. That means before oxidation, there will be enolization. There will be enol form. Now, there may be two possible enol which can be formed from this ketone. One is this, another is this. We can simply say that this enol is more stable due to more number of hyperconjugate structures, more number of alpha hydrogen atoms than this one, where in this case the number of hyperconjugate structures is only 2, and here in this case 6. So the reaction always proceeds via the more stable intermediate. So the reaction will occur not via this but via this, and with oxidative KMnO4, which KMnO4 acidic, which is a very powerful oxidizing agent, there will be oxidative cleavage across the double bond, as we have already discussed in alkenes chapter, and each portion will form corresponding alcohol, carboxylic acid. So this will give 1,2 acetic acid. This will give 1,2 acetic acid. So this 2-butanol, when treated with KMnO4, will finally give 2 molecules of acetic acid. The reaction cannot be stopped at this stage. If we want to stop this reaction at this stage, we have to either go for acidified potassium dichromate or acidified CrO3 or CrO3 in presence of pyridine. So ketones undergo oxidation via enolization, and it will be the more stable enol that will undergo the oxidative cleavage, giving the mixture of products. Let's take another example. Let me complete first, then I will explain. As we have already mentioned, that tertiary alcohol only undergo oxidation in presence of acidified KMnO4. In the absence of any alpha hydrogen atom, it will first, with acidified KMnO4, it will first undergo dehydration, forming this. Then with again acidified KMnO4, which is a very powerful oxidizing agent, there will be oxidative cleavage. This portion will give acetone and this will give carbon dioxide. Again further, when treated with KMnO4 present in the reaction medium, this will give acetic acid and carbon dioxide. How? Because this acetone will first form this enol, which will undergo oxidative cleavage, and this portion will give acetic acid and this portion will give carbon dioxide. I hope that now it becomes clear why tertiary alcohol with very powerful oxidizing agent acidified KMnO4 gives a mixture of carboxylic acids containing less number of carbon atoms than the original alcohol via the carbon-carbon cleavage. Now let's actually discuss the mechanism. The actual mechanism which we